Hello, students. Today, we're going to explore a very important topic in electrochemistry. We'll start by looking at a common experiment from your school lab, one that often raises a lot of interesting questions.
Have you ever wondered about this? It seems like such a simple observation, right? But the science behind it is actually fundamental to chemistry. Why on earth does salt water conduct electricity so well, while pure water or even sugar water fails to do so? This is the central mystery we are going to solve today.
So, let's begin our journey to unlock the secrets of electrolytic solutions. Now, you must pay close attention, because understanding this concept is absolutely essential. It's not just for your board exams, but it's also key to understanding practical things, like how we test the purity of our drinking water, or even how the electrochemical cells, the batteries in our phones and cars, actually work.
Okay, the very first thing we need to understand is this. The ability of a solution to conduct electricity doesn't come from the water molecules themselves. Not at all. It comes from the particles that are dissolved inside the water. And, as we will see, the specific type of particle is what makes all the difference. This brings us straight to the core idea of this topic. You see, in metals, electricity is carried by electrons. But in electrolytic solutions, the story is different. The flow of electricity is not due to electrons. Instead, the charge is carried by mobile, charged particles that we call ions.
We have all learned this in our physics classes, correct? If you have a metallic wire, like copper, the electric current is simply the flow of free electrons moving through the metal structure. It's a very straightforward process.
However, in a solution, the situation changes completely. Here, the charge carriers are much larger than tiny electrons. They are entire atoms, or even groups of atoms that carry an electrical charge. These are the particles we call ions.
So for your exam preparation, here is the clear and simple definition you should remember. An ion is an atom or a molecule which has gained or lost one or more electrons, and this gives it a net positive or negative electrical charge. For instance, when common salt NaCl dissolves in water, it breaks apart into positive sodium ions Na+, and negative chloride ions Cl-.
So what's really happening when we apply a voltage? Well, let's imagine the solution is like a crowded room filled with these positive and negative ions. The moment you connect a battery, an electric field is created. All the positive ions start moving towards the negative electrode, and all the negative ions start moving towards the positive electrode. It is this organized, directional movement of ions that we call the electric current in the solution.
To make this concept very easy for you to remember for a long time, let's use a simple analogy. I want you to think of the conductance of a solution as being just like the flow of traffic on a very busy highway. This analogy will really help you understand all the factors involved.
Let's map this out properly. The cars driving on the road, those are like the ions moving in the solution. The traffic density, which means how many cars are on the road, is just like the concentration of ions in the solution. The speed of the cars is analogous to the mobility of the ions, how fast they can move. And just like a wider road allows more traffic, the geometry of the container can also affect the conductance. So the main point is this: more ions and faster moving ions will result in a higher current. Simple.
So, you might ask, why did chemists even develop this concept of conductance? Well, the reason is quite practical. They needed a reliable way to measure and quantify this ion traffic. They wanted to know the concentration and the mobility of ions so they could predict how well a particular solution would conduct electricity.
All right, now that we have the theory down, let's see this concept in action. We'll start by finally solving our light bulb mystery, and then we'll look at a common piece of technology that you might even have at home.
Now we can finally solve our puzzle from the beginning. In a salt solution, there are many free-moving sodium and chloride ions, so the traffic highway is very busy. This large number of charge carriers allows a high current to flow, which is why the bulb glows so brightly. But what about pure distilled water, or sugar water? In these cases, there are almost no ions. Sugar dissolves, yes, but it doesn't break into ions, so the highway is practically empty. No ions means no current, and therefore, no light. It really is that simple.
This brings us to a very practical application, the Total Dissolved Solids Meter, or TDS meter. These devices are very commonly used to check water quality. And guess what? It works on the exact principle we just discussed. It has two small probes that apply a small voltage to the water sample. The device then measures the current that flows between them. A higher current means there are more dissolved ions, which means a higher TDS value. The meter simply takes this conductance reading and converts it into a number for us to read. For example, your regular tap water might give a reading of around 300 microsiemens per centimeter. This number is a direct measurement of the ion traffic in your drinking water, and it gives you a good idea of how much mineral content is dissolved in it.
Now, let's discuss a very interesting point, one that could be a tricky question in your competitive exams. You might think that if you keep adding more and more salt to water, the conductance will just keep increasing in a straight line, right? I mean, more salt means more ions, which should mean more current.
But actually, it's not so simple. At very high concentrations, the ions become too crowded. They start colliding with each other and getting in each other's way. This friction actually slows them down. It's just like a massive traffic jam on our highway. This traffic jam reduces their overall mobility, so the conductance doesn't increase as much as you would expect. This is a very important nuance to remember.
So, we have covered a good amount of ground today. Before we finish, let us quickly recap the main points into a simple exam toolkit that will help you remember all of this.
First, the core idea. Conductance in electrolyte solutions is all about the movement of ions. Second, the mental picture. Always remember the traffic highway analogy. More ions, or cars, lead to more current, or traffic. And third, the real-world example, the TDS meter, which uses this very principle to check the quality of our water.
So, my final advice to you is this. Just remember these three things: the core idea, one clear mental picture, and one practical example. If you can do that, this entire topic will feel much, much lighter for you during your exam. Keep these points in mind, and you will be able to confidently answer any question on this concept. All the best.